Hello. The next application we want to talk about is linear motion. Information about motion is in the textbook, but it's not in one particular section. It's kind of spread out as examples and applications in different parts of the book. So we try to gather together all of the important information in one lecture here. So we're going to talk about position, velocity, and acceleration. And I should mention that physics is Isaac Newton studying gravity and the motion of planets is one of the reasons calculus was first developed. So motion is one of the more natural applications and probably one of the more important as well. We're going to consider a position to be on a one-dimensional number line for now. If you want to think about motion in the plane or in 3D space, we'll talk about that in Calc BC or special topics. So right now we'll just have single variable motion, and we can use either x or y or s for the name of the function. And if we use x of t, don't be confused. X is now the dependent variable, and the independent variable t is time. Okay, so the rate of change of position is the velocity. It's a natural definition you probably are familiar with. And the rate of change of velocity is the acceleration. Now, what can we do? We have to be careful to distinguish between velocity and speed. Velocity has a sign. It's either positive or negative. And we'll think about positive velocity as moving to the right, negative is moving to the left. Speed, on the other hand, is just the absolute value of velocity. So it tells you how fast the particle is moving without caring about direction. This is a common blundering point. If you're looking at the acceleration and you see the acceleration is positive, well, we don't know if the speed is increasing or decreasing. We know the velocity is increasing if the acceleration is positive, but if the velocity is negative and increasing, that means the speed is getting closer to zero. So speed is only increasing if velocity and acceleration are the same sign, both positive or both negative. The other common stumbling block is thinking about total distance traveled versus displacement. Displacement is just endpoint minus starting point. We don't care how you got there, we just want to know the difference in those two positions. You can have zero displacement, just means that you finished where you started, even if you traveled around the world to get there. Distance traveled is never negative, it includes total distance, even if the particle reverses directions. So if you start at 0.5, move to 8, change direction and finish at 3, your displacement is -2, right? 3 minus 5. But the distance traveled, well, you moved 3 units to the right and then 5 units to the left, so total distance traveled is 8. Okay, let's look at one example which would be similar to the kind of question we might ask you. Suppose you're given the position function, and let's say it's this nice cubic function. So we can find the velocity, just take a derivative, and I can factor this quadratic. So the velocity is 6 times 2t minus 3 times t minus 3. And we can analyze that to say velocity is negative only when t is between 3/2 and 3, the zeros of that quadratic function. So only when the velocity is negative is the particle moving to the left, and the particle will be moving to the right otherwise. Taking one more derivative, we can find the acceleration, and we can see the acceleration is negative when t is less than 9/4, and otherwise the acceleration is positive. So it's easy to talk about the velocity. Velocity is decreasing when acceleration is negative, and otherwise increasing. But the speed is only increasing if acceleration and velocity are the same sign. So if t is bigger than 3, then both the acceleration and the velocity are positive, so the speed is increasing. On the other hand, if t is between 3/2 and 9/4, the acceleration and velocity are both negative, so the speed is also increasing. Otherwise, the other intervals, the speed would be decreasing. Finally, we can talk about displacement versus distance traveled, the particle changes direction at 3/2, and the total, it also changes directions at t equals 3, but so let's talk about the total distance traveled on the interval t from 0 to 3. So the total distance traveled is the difference in the first from 0 to 3/2 plus the net displacement in the second from 3/2 to 3. So plug in these values for t, add up the numbers, you should get 81/2. The total displacement is just s of 3 minus s of 0, which is 27. So total displacement should always be less than or equal to total distance traveled. And we can see that happens in this case.